All right. So again, if you've got any interest in being a TA for next semester for 2168, please let me know. Also, it really just depends on the needs, but I definitely need one for 2168, and I'll keep anybody else in mind for anything else or pass you on if I can't have, but come and speak to me about that. Now, this lecture, as I previously mentioned, we're just going to be going over basically we're going to be reviewing for the final exam. In the GitHub folder, the GitHub under pages, right, under the GitHub class link, right, hopefully you've checked it out by now, under class, right, under the data structures folder in there is a thing called study guide, right, which I wrote actually last year, because my students asked for some guidance on the final exam. So I've got a list of basically the major topics that you'd want to be making your notes about, right? This isn't really telling you anything other than what to know about, but like sorting, hey, I covered a lot of sorting, but specifically I'm interested in insertion sort, quick sort, and merge sort, how to do Huffman encoding. Right, data structures for the exam, you will not write any of the data structures, but you will need to know how to write code that uses them, all right? So almost everybody takes the same exam, which is to say that everybody but you guys will be taking the same exam. You'll be taking almost the same exam because you're at a different because you're being in a different section that comes at night, right? So you are not taking it during the final exam period. You are taking it in the evening because that's at least the way I have been told that it happens, because we can't make the assumption that if you're in the evening class, we have to make the assumption that you can only make it on evenings because you might be working or something or another. So I've just simply gone over a lot of these things, but most important links are these 4 over here, which are for 4 exams from other institutions. Now, one of these from Uppsala University is more for an algorithms class, but because of the way these curriculums can be made and differences in curriculum, some data structures in algorithms or algorithm data structures class or whatever they're called, they have some crossover with what we learn in data structures. So this one, there's plenty of stuff in here that you're just going to be going, what in the world is going on here? But there's some questions that like are graph related that you will probably be able to understand, right? As you can see by the notation over here, that it's way more mathematically, intensive. So, also, let's see, do I have one here? Also, one of my favorite links from here that I just did not make it onto here. Let's see. Let's go and look at my bookmarks. Bookmarks toolbar. Academia, teaching, exams. Right. This one is from. So I like this one. This is a graduate entrance exam to Tokyo. It's a University of Tokyo, which is like Tokyo's, big university. Sorry, it's like Japan's most prestigious university. Anyway, so this is like an entrance exam to get into the graduate degree program there, right? So let's just take a look at it for a second. Problem 1 is basically testing your ability to do, vector, this is a previous entrance exam. It's like, can you do vector algebra? Can you deal with matrices? Did you learn, are you able to go on to like the graduate level mathematics that they think is important, right? Problem 2 is on non-deterministic finite automata, which I kind of described with some people one day. We went over 5 minutes, and people kind of understood the concept, but it's in a specific class that's not this, right? So class that's not this, class that's not this. Problem 3 might look fairly familiar. Consider the problem of sorting an array of integers using the heap sort algorithm. Assume that heap sort brings the minimum element to the front. Answer the following questions. 1. Heap sort consists of 2 phases. explain is what to be performed in each phase. So what are the two phases of heap sort? Heapify is the first phase, and what's the second phase? I mean, it's not really got a name, but you can describe what it happens during. Yeah, you bubble it up. You essentially sort. You put the numbers in. Yeah, phase 1, turn it into a heap. Phase 2, use the heap to turn it into turn the heap into a sorted array. So consider sorting of the following array using heap sort. Again, English not necessarily the greatest there, but they're saying you want to heap sort this array, okay? What is 3, 8, 1, 5, 4, 9, 7? Consider the structure. Draw the structure of the heap just after the first phase, right? So let's start off that array, right? 3, 8, 1, 5, 4. Right. Let's get some. 3, 8, 1, 5, 4, 9, 7. Right. So the way the heapify phase works is that we start from the bottom and push stuff down, right? That's how heapify works. If you wanted to do an O of n time, rather than adding one item at a time to a heap, which would take n log n time, the heapify phase you push down items, right? And it's a max heap that we're building. So, but fortunately, heapify is really simple as a result of pushing down. I can't push down 7 any further, can't push down 9, can't push down 4, can't push down 8. So we're done with the bottom row. That's more than half the items done right there. Okay, 1, right? The smaller items need to be pushed down, and the heavier items need to bubble to the top, right? So 1 needs to be pushed down. It's got 2 bigger and the parent needs to be the biggest thing in the subheap. It's got 2 bigger parents, so we swap with 9. 1 can't be pushed down any further, so we move to 8. Again, 8 is bigger than its children, so we don't need to push it down any further. And then 3, it's smaller than both its children, and the biggest thing needs to be at the top, so we push down. So we push down 9. So we push down 3 and swap it with 9, and then 3 needs to be pushed down again to swap with 7. Right? That's how the push down. Right? And it's weird because we're using a max heap here rather than a min heap. Right? Max heaps are always weird, like that. Answer the time complexity of each phase when sorting with an array of length n. Explain the reason. So, stage 1 for heapify is O of n time, because we're starting from the bottom, so we essentially get half the array for free, and then we get basically half the array is done during our first step. There's a better write-up, I think, in the book about how that works, but I want to move on because that's not really something I'm going to be talking about too much. And the second phase is, right, we basically pop off a number and we take something off the top of the heap and put it on the back of the heap, right? Take the biggest element and put it in basically the rear of the array. You do that n times. Each of those steps takes log n time, so its total runtime is n log n. So heap sort is n plus n log n, which gets simplified to big O of n log n, right? So, and that actually goes ahead and answers the fifth question, which is the execution time of heap sort on modern computer systems is often longer than some other sort algorithms, such as quicksort and merge sort when sorting a large array. Please explain a possible reason. Well, other algorithms don't have to deal with that heapify phase, right? You've got that added time in there. Also, there's a lot of swaps that need to be done and a lot of comparisons that need to be done. You're comparing against, whenever you're about to swap something, you actually have to compare against 2 items as opposed to 1, right? You have to compare up against both your children. Whereas in the other algorithms, when you're going to be swapping something, you have to, you only compare against 1 thing, right? Here you're comparing against 2 things, and then you have to decide which is the smaller one. So there's a lot more comparisons that go on. Right? This is a graduate level exam, and a lot of you could have gotten like most of that page. Yes?
So what would the time complexity be?
Oh, sorry. I must have skipped 4. Or answer the time complexity of obtaining a sorted list of the smallest k items from a length of an array using heap sort. Explain the reason. Oh, I didn't go over that one. So heaps, one of the interesting things about heap sort is that you can use it to grab just the smallest items from it. So let's see. I mean, so let's think about that for a second. The smallest items, like say we're trying to get the smallest 4 items, they're all at the bottom, right? But they're unsorted, so then we'd have to sort that, which kind of defeats the purpose there. And honestly, I'll be quite honest, the reason for it eludes the strategy there eludes me right now. But I remember basically it's like log n. It's like what? It's like k log n that it would take, I believe, for number 4. I just can't remember for the reason, or even that's right. It's probably completely wrong, and somebody's.
Well, if you did it as a min heap, wouldn't it be k at the end instead of n?
If you put it as a min heap, things aren't going to be sorted necessarily in the heap, right? But let's see. But using your idea, say we generate a min heap, right? Smallest design at the beginning. So we do k removals, and the back half of the array would be then, say we get the same array. Once we do say we're looking for the 3 smallest items. Once we use your strategy, what you're saying is essentially we'll get 1, 3, 4, and then an unsorted mess over here, right? And then we could technically read in O of n time this section of the array, right?
K.
Which would be k. So this would take O of k time to do.
Right.
So it would be k log n plus k in that strategy, which is fairly straightforward, right? That's an answer, right? So this is a graduate exam. Again, I bookmarked it like a year ago, and I haven't even looked at it. So other than to say that, it was a heap sort problem. Maybe I'll steal it for a final exam some semester, right? Probably not for you guys though. So but this is the kind of stuff that's considered important for understanding computer science, right? Right. So data structure, but heap sort's a very powerful algorithm because of that kind of ability over here for number 4. Let's go on. So let's go on to what we would see a practice final. I'm a big fan of this practice final exam. It has very good questions. This one's from Harvard. It has 3 parts, multiple choice, excellent multiple choice questions here. Part 2 is basically has some stuff that you'll see on the exam, and then part 3 consists of basically a single problem which you must complete. It's coding. So you have 2 hours. So this is a 2-hour exam. We should be able to knock it out in about an hour, minus the problems that we did not cover in this class because we covered topological sort. Yeah.
The Harvard exam or the actual final?
The Harvard exam. You should be able to knock it out in an hour. Your final exam, you should be able to. Again, you'll get 2 hours for that. It is also open book and open note, just to reiterate. And I don't know where the rest of the finals will be, but your final exam will be here, right, in this room. Yes.
Does the open book include, if we have the copy of the text
if
on
it
the laptop?
Paper. You can print it out if you want to, but you can borrow a copy. You can arrange to borrow a copy from somebody else in another section, but paper. You can print out the slides. I just can't let you use electronics. Worst case scenario, screenshot the relevant pages and print those out. Honestly, the open book is more of a hindrance than a help, I find, right? Because your best strategy is to just, write yourself some notes and then work from there. And write as many notes as you need to make them clearly legible, right? Yes?
Also, have you linked the...
It's already linked online under study guide in the destruct folder. It's been there since the very beginning of the semester, actually. Okay.
On GitHub?
Yeah, on GitHub.
Oh, okay.
On the GitHub link, right? So, all right, multiple choice, 3 points each. So here their policy is actually one I'll probably need to adopt on an exam if I do more multiple choices on an exam, which is that you can choose two answers, label your first choice, and label your first choice. If your first choice is wrong, we'll give you partial credit for your second choice, right? Which is a pretty good policy, right? So let's start with this one. Suppose items A, B, C, D, and E are pushed in that order onto an initially empty stack. The stack is then popped 4 times. Each item is popped off and initially inserted. It is initially inserted into an initially empty queue. We remove 2 items from the queue. What would be the next item from the queue? Right? If you've been trying to follow that, in your head, don't. That's a bad idea. Instead, of course, the correct answer is to draw it. Like anything else, that's kind of confusing, right? So let's draw ourselves a stack. Right? It says that we are going to push A, B, C, D, and E onto the stack. Right? Then we have a queue here, and I'll just simply create an opening here to represent the front of the queue. Right? So it says then we are going to pop it 4 times, and every time we pop it, it's going to be inserted. That item goes directly into the queue. So E, D, C, B. Right? If 2 items are then removed from the queue, where do you remove from the queue? From the front. So remove 2 items. What is the next item that will be removed from the queue? C. Right? This one's pretty trivial if you know that basically that if you remember that stacks are LIFO, queues are FIFO, and you actually decide to draw it. Right? If you try to do it in your head, I mean, you could do it. It's just not fun. Right? Right? So if the binary tree below is printed in a pre-order traversal, what would the result be? Okay, so pre-order means myself, the root, my left subtree, then my right subtree, right, in that order. So here, what should be the first item if this is pre-order? 6. So that immediately rules out A and B, right? So, so then the next item in the pre-order traversal should be 17, right, and then 9, and then 4, right? Myself, my left side, which then goes myself, my left side, which then goes myself, my left side, my right side. Then this goes my right side. So it should be 6, 17, 9, 4, which means that only these really match. Although, interestingly, if we look at D, we get 6, 17, 22, 9, 4, 16, and 12. Which is a very interesting traversal. It's what's called a level order traversal, or as we've learned it, a breadth order traversal, where basically it went to the root, then the next level, and then the neighbors of the root, right? Level order traversal. And the way you do a level order traversal is not by doing recursion, but by using a queue, right? Just like you would for breadth first search. So keep that in mind because this is one of those things that comes up that will be coming up later on this practice exam. So a graph implementation uses a 2D array to represent edges would be most reasonable for which of the following cases? So let's discuss. There are 2 ways. Yes?
Sorry, the level order traversal, did we go over this before?
Nope. Except that we kind of did in the form of breadth first. Level order is the same as breadth first, right? It's just a specific name that when it's used for a tree. We have not gone over it formally though, right? But okay, so I mentioned in the lectures that there are 2 ways to represent a graph, right? What are the 2 ways we can implement a graph in, as a data structure? Yep, an adjacency list or adjacency matrix, right? An adjacency list to review, that's just simply us. That's just simply having a kind of a map or an array, right? And basically we say, like, node A is connected to, it has links to all these nodes. It has, node A is connected to B, C, and D. Node B is connected to C and F, right? C is connected to, let's say, it would also it would be ACF here because, right, if it's a undirected graph. Right, and C would have its own list of nodes that it has edges with, and so on and so forth, right? You have the node and the nodes it has edges with, right? That's an adjacency list. It keeps track of the node. Each node keeps basically we have a data structure which says for each node, here are the nodes we're adjacent with, right? The other way to store a graph, which is a bit easier for our eyes to parse, is an adjacency matrix, right? Which just looks like a matrix, right? A, B, C, D, A, B, C, D, right? And here in an unweighted graph, you would have a 1 to represent an edge, or a 0 or blank to represent the presence of no edge between them, right? So if there was a 1 here, this would mean there's an edge between B, going from B to C. Okay? Let me just put those headers on there. Right? So you've got two ways of doing it: adjacency list and adjacency matrix. Okay? Now, does anybody remember why you would want to use one over the other?
Dense graph with the matrix.
On the dense graph, you want the matrix. On the sparse graph, you want the adjacency list. Now, why is that? Because in a graph that's sparse, and sparse and dense refers to the number of edges in the graph compared to the number of nodes, right? So if you don't have too many edges, right, then it's easier than if you were using a matrix, you'd have basically a bunch of empty spaces, right? On the other hand, if you've got a bunch of edges, then like this, then this suddenly becomes a much more efficient structure to use rather than the adjacency list, right? Less memory is wasted here than you would with the list, and the lookup is quicker. Now, the difference, there's a magical cutoff point. We want to use an adjacency list when when less than 25% of the all possible edges exist, and we want to use an adjacency matrix when more than 25% of all possible edges exist. Right? So use a matrix, and that's what defines a sparse or versus dense graph. Whether it's less than 25% filled of possible edges exist, or more than 25% of all possible edges exist. Right? By the way, this is a 4x4 graph I'm defining here. That means there's 16 possible edges, right? And because it is legal for a node to point to itself. It's illegal to be in a relationship with itself there. So let's look at that and apply that knowledge to here. We have 1,000 nodes and 1,200 edges, right? So that's 1,200 edges out of a possible 1,000 times 1,000, which is 1,000,000. So 1,200 edges out of a possible 1,000,000. That's that's a pretty sparse graph. 100 nodes, that's 10,000 possible edges, right? 4,000 out of 10,000, that's 40%. That's considered a dense graph. So that's probably our answer. 1,000 versus 10,000, again, 10,000 out of 1,000,000 is a small percentage. And then finally on D, we've got 10 nodes, 20 edges, which means we've got 20 edges out of a possible 100, which is close to being dense, but not quite there yet. So our best answer is D, and E is just a red herring, because it's saying, oh, you can't have an adjacency list. That's not a thing that actually exists. Well, adjacency lists are a thing that exists, so E is just plain wrong. All right. This is another good problem because it's the type of problem I hated going over as a student, right? So here's a binary tree, public class node, and a node here. Here they didn't teach how to use generics. That's one of the things I spent I consider useful because you should understand how to use Java. So public class node, nodes have a value and they have a left and right, node, right? So instead of just having an E, they only hold integers, right? So let's consider this following method. Public static node mystery, which takes in a root of a tree or subtree. If my right child is null, I return myself. Otherwise, I return mystery of my root child. So you consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what this method is supposed to do. when passed a reference to the root node of a binary tree. Text Consultant 1 says it returns the last node that gets visited by an in-order traversal. Consultant 2 says it returns the last node visited by a post-order traversal. And Consultant 3 says it returns the last node visited by a level order traversal, right? Level order traversal being the thing we just mentioned, a breadth first search. Which of these opinions is correct regardless of the contents of the tree? All right? So first, let's discuss what this method actually does, right? Okay, let's talk about what this actually does. Right, here's my node, right? And if I've got a left subtree and I've got a left subtree and a right subtree, really don't care about the left subtree for this. If my right subtree is null, I return mystery of root.right. Right? So if it's not null, it returns mystery of root.right. Otherwise, I return myself. So what this will do is that this will effectively keep traveling to the right until it hits the rightmost node, which it returns. Okay? So this will return the rightmost node. What's special about the rightmost node in a binary search tree? Yes? Yeah, it seems kind of obvious, so I'm pretty sure that's a lot of reason why other people didn't mention it. But yeah, that's exactly it. It is the largest node in the tree. That's kind of important. It's the largest node in the tree. That's really valuable for evaluating whether this is correct or not. So opinion 1 says it's the last node visited by an in-order traversal. Yes?
So I'm confused. The rightmost node is the largest node. Do you mean levels? What do you mean by large?
Like it's got the largest value in a binary search tree. The rightmost node has the largest value in the tree, right? Largest node, sorry. Oftentimes when we're talking about stuff like linked lists or anything that has nodes, it's really easy to conflate the item inside of it and the structure inside of it. And everybody, and it's important that I don't conflate that, but you'll find that everybody does it, unfortunately. Okay, so the last node visited by an in-order traversal, right? In an in-order traversal, that prints all the items in order, right? So it will print them from smallest to biggest. So the last item will be the biggest item. So that opinion is correct no matter what, right? The rightmost item is the biggest item. It's going to be the last node visited by the in-order traversal. Number 2, it returns the last node visited by a post-order traversal. What's the last node visited by the post-order traversal? Always? It's the root. The root. And the root will only be... Yep, the root will only be the last item in a post-order traversal if this is your tree. No right child, right? So 2 should probably review his data structures, right, before offering an opinion. And now opinion 3 says it returns the last node visited by a level order traversal. And on the face, that seems like a correct opinion, but obviously, since I said on the face, it's not a correct opinion. So, right, because if you draw yourself a perfect tree, right, it will return a level order traversal, which will start here, then do breadth first, right? So it'll start here, then go this way, then go across the bottom, right? It will return that. But what if I added an additional node over here well, it's still perfectly fine, right? What if I removed this node? Then for a level order traversal, then our function will return this node, which is not the last item returned by a level order traversal.
But wouldn't the level order traversal when you had that lower one, wouldn't that come out afterwards?
It would come out afterwards. So yeah,
That was no good either.
yeah, that was no good either. So basically anything that was not perfect, it would be incorrect. So only opinion 1 was correct, regardless of the structure of the tree. 2 and 3 could possibly rewrite some of the time, but 1 was the only one that would be correct all the time. So poorly chosen hash. So if you have a poorly chosen hash function, it is possible to have a situation in which the search time for a hash table of n items goes to O of n factorial, log n, O of n squared, or constant time. So which of these is correct? When we have a poorly chosen hash function, it's possible to have a search time in which the hash table of n items goes to what? O of n, right? That is the worst case scenario, right? Suppose my hash function is something like h of x, where x is our key, is equal to 0, where everything goes now to the 0th index, right? Let's draw what happens there. So we put in our first item, and there's no collision, right? But put in our second item, there's immediate collision, but we'll take this space. Put in our third item, collision, collision, then take this space. Fourth item, collision, 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 take this space. Collision, 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 take this space. Collision, 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 take this space, right? Poorly hashed. So if we have a poor hash function, and you already have n items in it, then O of n, then basically, sorry, if there's already n items in this array, a bad hash function would mean that basically it could take up to O of n time, right? We could have a collision for every single item we've already had in there. Although technically, with the way this question is worded, E is correct, technically, if it's justified, constant time, because you could have a constant time search algorithm even with a very poor hash function. It is possible, right? Especially if it's the first item. But I mean, but
It could also happen.
but that's just but that's not the intent of the problem.
Couldn't it also happen?
Technically, because of the way big O notation works, but I'm pretty sure that's not the intent of what they were going for. I'm pretty sure they're saying, it's possible that the search item goes that as the issue with that. Anyway, let's go ahead and look at this. We've got 6. So I already blatantly stole this question on our first exam, which is that we've got a linked list, right? Here's the data, here's the next, here's the previous, right? We've got a node here, n, we've got a node here, p, and we've got a third node that's just not, we've got a variable for it. Which of the following expressions does not refer to the third node in the list? Okay? So, for instance, p.next is the third node. So let's look at the other ones. p.next.next, that's also the third node. p.previous.next, that's p, right? So that's our answer. But let's just go ahead and do the others. p.next.previous.next, that's the third one. The biggest problem in this one is that you can accidentally, misread a previous or a next. And then let's look at this. n.next.next.previous.next. Right, that's the third one. So our answer was C there. Now this one's very good because it's very much like the scenario questions I like asking, like which is the best data structure to use. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets so you can quickly determine whether or not the given license plate number is in the database. In other words, is this person a bad driver? Spoiler, everybody's a bad driver. So speed of response is very important. Efficient memory use is also important, but not as important, right? So we care about the speed. That's the most important thing. But we also care about memory, just not as much, right? And this is the typical thing you run into, that we care about speed, we do care about memory, but just not as much. Okay? So which of these data structures would be the most appropriate for this task? A, a sorted linked list. B, a sorted array with 1,800 entries. C, a table using open addressing with 1,800 entries, 3,600 entries, or 10,000 entries. And I'm going to assume here that by entries they mean table size, right? This is the size of the table that we're creating, rather than the amount of entries, because they said they want 1,800 license plate numbers inside it. So that's how many entries you're going to have in it, right? I assume that they mean the table size over here, right? All right, so let's start with a sorted linked list. So actually, we've got the sorted linked list and the sorted array. So if you've got a sorted list or a sorted array, what's the algorithm you want to use to search for something in that? Right, there was an algorithm we learned in the recursion chapter. Yes? Binary search. Binary search. So binary search, if you remember, is the algorithm for basically for finding the smallest item in a sorted array, right? Look at the middle, right? Is the item I'm looking for higher or lower than the middle, or is it the middle? If it's the middle, I'm done. If it's lower, then just search the lower half. If it's bigger, search the upper half of the array, right? That means you can cut out half, So you can cut out half the search space each time you do it, right? So let's just consider B for a second, a sorted array with 1,800 entries. That means that we could do it in, we could search for our item in log of 1,800 time, log base 2 of 1,800. So however many times we can split 1,800 in half, that's how many steps it will take on the worst case to find something in there. But this is log of it. This is a log of n algorithm, which is pretty darn speedy. It's also, because it's an array that's exactly as big as the number of items in it, it's also the most memory efficient. So if we cared about memory, if memory was the most important parameter, more important than time, then this is what we would use. Okay, a sorted linked list though is wrong always for this, because doing binary search over a linked list is kind of torture, because you have to iterate all the way to the middle, takes often time, then iterate all the way to the middle of the sublinked list, and then all the way to the middle of that, and all the middle, right? Because you can't just jump between indices in a linked list. You can in a sorted array. Looking up this something in here would take O of n time for a sorted linked list. So let's take a look. Then let's look at hash tables. So we know that hash tables we will get constant time, ideally. But if we have 1,800 entries and our table size is 1,800, that means what's going to happen as a result if all the spaces in our hash table are filled up? There's going to be a lot of collisions, right? There was a formula that you can remember, that you can look up, but I'm not going to pull it up right now because you're not going to have to remember for the exam, right? So, but there's a formula that simply states, like, depending on how full it's filled up, this is the number of collisions you're going to get, right? And you will be getting a lot of collisions when it's completely filled up, right? The parking lot analogy still applies, right? If you're looking for that one item in a parking lot, right, or that one last space in a parking lot, it takes a while to find that last space. On the other hand, if it's twice as big, right, that means it's half the way filled up, which according to if you remember, that means that we've got the expected number of collisions we're going to get is 0 to 1, right? We can solve it with one probe or two probes, right? So with 0 collisions or 1 collision, right? So it's very fast. So 1 or 2, we'd expect 0 or 1 to 2 checks with this one, which is quicker than whatever log of n can produce. Unfortunately, we are wasting half our space, right? We'll still be getting, and we'll get basically, slightly better time, like the difference between, but suddenly upping this to 10,000 entries doesn't give us Usain Bolt level of speed. It doesn't. It's not much of a difference, and we're wasting way more memory now to do that. So D is the best answer because it strikes that balance between speed, constant time speed, while it's not wasting too much memory, right? If you only cared about speed, then E would be the best answer, but we don't just care about speed. And if you only cared about memory, B would be the best answer.
And what was the C? What's the estimated?
So the estimated number of collisions, let's see. I think that's up on our slides, but the formula was, I cannot remember off the top of my head, but I think it was something along the lines of 1, and again, I'm going by memory. It's 1 plus 1 over 1 minus L, where L is the current load factor, right? So that would be kind of, that would be let's say it's let's just go to endpoint 0.099, because otherwise we're dividing by 0, and that's a bad idea. So 0.99, that'd be 1 over 100. It'd be, yeah, it would be 1 over 0.01, which would be over 100. 1 over 100, which means we'd be getting 100 lookups, which is not good. According to that formula, which I may have just pulled out of a hat or something, right? But right? But again, the formula is in the book, and I did not memorize it. All right. So let's go over here. Huffman trees. A Huffman tree is constructed from a text document containing 5 characters. I'm definitely going to use this question on quizzes.
Can I say one thing? At 75%, what is our expected?
Like at 7, so at 50%, it's like one to 2. You've got 1 to 2 probes, right? Which means you've got 0 to 1 collisions, and at 75%, it's like 2 to 3 probes.
Okay.
A Huffman tree is constructed from for text containing 5 characters. If the character E appears the most frequently, and then the character I has the next highest frequently, which of these 3 could be the Huffman tree for that document? So first of all, one of these things is not like the other. One of these things is not a Huffman tree. Which one is it? One of these it clearly violates a big property that we have in Huffman trees. Yes? The first one. What does it violate? Right. Leaves. Yeah, they're not leaves. Right? You can, in a Huffman tree, you can only have values in the leaves. Right? You can only have values in the leaves of a Huffman tree. So 1 is not a Huffman tree. 2 and 3 are Huffman trees, though. They're perfectly fine. So now let's go ahead and talk about that. E is going to be the most frequent character, then followed by I. So which one of these is where E is represented as the most frequent character? 2. The most frequent character has the least number of bits allocated to it. Right? So here you've got, here E only has 1 bit, whereas here it'd be the least frequent character because it's got 3 bits allocated to it. And ostensibly, yeah, I could have the same weight as the rest of these fellas because the second most frequent character might not be that much, right? Like suppose this, like E appears 1,000 times, I appears 100 times, and these each appear 50, right? This would be a perfectly, this would be a, probably not that tree, but E would be up here, whereas I would be much lower. All right, so, heap sort problem. An array of 7 integers is being sorted by the heap sort algorithm. Once we do phase 1 of the algorithm, right, the heapify structure, which of the following is in order for the array? This question is actually asking a completely different question. It's a convoluted way of asking which of these is a valid max heap, right? Because when you heapify, you turn it into a max heap. So obviously, D is wrong because that's not a max heap because the biggest item's not at the top. And before you have to double check, all of them are, right, all of these have the same values in them, right? So the professor's not here is not being a total jerk and like changing a digit somewhere on you. That would be really terrible. So we're asking which of these is a max heap. So 85, right, its children are 78 and 45. So then that's perfectly fine for a max heap. 78, it's bigger than both its children, and 45 is not bigger than both its children, right? It's not. 45 is smaller than 47 and 49, so A is not a max heap. 85 is bigger than both its children. 49 is not bigger than both its children, 45 and 47. Wait, no, it is. Sorry. 49 is bigger than 45 and 47. 78 is bigger than 51 and 53. So this looks perfectly fine. So 85, bigger than both its children. 78 is bigger than 45 and 47. 49 is not smaller than 51 and 53. Right? How am I doing this? Right? Remember, I'm just simply using the formula, which is pretty easy over here. Right? My children are located at twice my index plus 1 and twice my index plus 2, which is pretty easy to see. This is levels. This is the first level. This is the second level. This is the third level. Right? There's only 3 levels here because there's only 7 items. Right? D is wrong, and then of course E is also wrong because 51. His children are 53 and 49. 53 is bigger than 51, so this isn't a valid max heap. You can, of course, draw this out for yourself, and I would recommend doing that. I just happened to be lazy and wanted to sit down for a second. So this is also another question which I need to totally steal for an exam or something, because I only have to draw, because here I can say, here's a tree. Right? Here's a binary search tree. Which of the following input sequences will not produce this binary search tree? Okay? So here we're just saying which of these is a valid way to build a tree, right? Which will result in this shape tree, right? Obviously, these all have the same numbers that are on here. So this is all about the shape, producing this shape. For instance, let's look at A. You insert 5 first, then 3, then 4, then 9, then 12, then 7, then 8, then 6, then 20. All those nodes were inserted in such a way, in such an order that basically it would produce this shape. So let's look at B. 5, 9, 3, 7, 6, 8, 4, 12, 20. Look at C. 5, 9, 7, 8, 6, 12, 20, then 3, and then 4. Let's look at D. 5, 9, 7, 3, 8. That's fine because 8 came after 7. 6, 12, 6, 4, 20. So that's fine too. So the professor was a jerk and made us go all the way down to E before we could find the last one. 5, 9, 3, 6. That will result in a completely different tree because 5, 9, 3, then 6 would go over here instead of 7 over there. And then 7 would go over here, and then 8 would go over here. Right? That produces a completely different result. All right, so 3 problems here. This part's not really too relevant for our exam, but I'll simply go over it. So suppose the keys in the middle row of a standard keyboard are, ASDF, GH, JKL, so an American standard keyboard, right? We just simply insert those values into a tree, empty binary search tree. Let's draw the tree after the sequence of insertions has been made. So let's just draw this tree really quickly. It's a very boring tree, or very exciting if you're really into trees. So A is first at the root. S, right, and we're doing this alphabetical order. That's why S comes after A, so it goes to the right. D, okay, right? D is greater than, it comes after A, but before S. Then F, and now here's where it's getting boring. F, G, H, J, K, L, and I'm done. Okay, so, right, it's a bit of a, right, turns out that those aren't all in order. Never really noticed that before that question, right? So that was a pretty easy one. Part 2, so that's an easy 7 points there. Part 2 was one of those questions where I say we're just going to skip it because we haven't just gone over it. We mentioned it very, very briefly when we did one in-class exercise, which is that we're saying, suppose the keys on the middle row of a standard keyboard are inserted into an initially empty 2-3 tree, which is a self-balancing tree, right? This is a tree that helps maintain its balance, right, by having 2 nodes and 3 nodes, right? We never learned how to do that, and if you're trying to find practice problems like that on the exam, just skip it, right, because that's not something that we've concerned ourselves with, right? So that's why, right, we only have so much time, and I use that time instead of teaching about 2-3 trees to teach you about generics and how to do topological sort and other different things that basically, we all have different priorities, but we all cover the same core material.
That was the ON worst case tree, right?
Yeah, that was like a worst case O of N tree right over there that we drew for the first case. All right, now this one is extremely useful because we definitely ask something like this on the final exam, right? So if you're wondering what kind of hash table question you're going to get on the exam, you're in the evening question, so I'm going to give you a coding question on the exam. But I'm also going to give you this, right? And the common final gets this kind of question as well, which is, show me that you can handle collisions. You are given an empty tree, you're given an empty hash table of size 7 that uses open addressing. The following sequence of keys is to be inserted. 15, 17, 8, 23, 3, 5. Insert these keys using each of the following approaches. If we get an overflow, in other words, if you've got collisions, right, indicate the element that causes the overflow. It doesn't really tell you how to do that. The professor is probably telling you to imitate him. So just, and on our exams for questions like this, we will give you pretty explicit instructions on what we want you to do. But let's look at this. So we're inserting these items with these keys, and here's our hash function. Hash of the key is equal to the key mod 7. And we resolve our collisions using linear probing, right? So we're using open addressing with linear probing for part A. So let's draw our table. 0, 1, 2, 3, 4, 5, 6. Okay, now, linear probing. So the first thing we need to do is insert 15. Insert 15, the key of 15 into this hash table. How do we know what space to put it in? Well, the hash function says insert it into 15 mod 7. So what is 15 mod 7? 1, right? So it should go. So 15 goes into index 1. That's it. That's as simple as. So this is a pretty simple problem. It looks weird, a bit weird, but it's fairly simple and straightforward. 17. So we need insert 17. What is 17 mod 7? 3. 17 mod 7 is 3, so we're going to put 17 over here. 8 mod 7. 8 mod 7 is 1. We would put it here, but we can't because it's already occupied. So linear probing says to do what? Yep. Step over one space to find step over and look for the next available space. So the next available space is 2, so we'll put 8 in index 2. Right? So now 23. We need insert 23. What is 23 mod 7? 2. 23 mod 7 is 2. So we'd insert 23 here, but we can't. So we look for the next available space, but can't put it there, so we look for the next available space, assuming you can draw curves correctly, right? So we put it here in this one. Insert. So now we need to insert 3. 3 mod 7 is 3. That's fairly easy math over here. So we're going to put 7 into index 3, but we can't. Sorry, we're going to put 3 into index 3, but we cannot because it's already taken. Then so look at the next space. Can't put it there. Look at the next space. We put it over there. Finally, put in 5. 5 is taken, so put it in index 6. Okay? So that's linear probing, which is what we care about. But let's just look at how we do it with quadratic probing, right? With linear probing, if we wanted to insert into index I, we first look at, if we can't put it in index I, we try to put it in index I plus 1, then I plus 2, then I plus 3, and then I plus 4. But with quadratic probing, what we say is that if we can't put it in index I, we try to put it into index I plus 1 squared, then into index I plus 2 squared, then index I plus 3 squared, and I plus 4 squared. Right? This ends up allowing us, and of course wraparound is a thing, right? So what this allows us to do is basically, this spaces it out a bit more, so it will hopefully result in less collisions. However, you now have to, we have a multiplication operator to do, which actually makes it a bit more expensive. So let's go ahead and see how quadratic probing works. Because I have mentioned it a couple times. Okay, x mod, so now we can reuse our first answers, right? 15 is supposed to go into here, 17 is supposed to go into here. Right, 8 needs to go into, 8 tries to go to index 1 as well, but it can't. So it looks I plus 1 squared space away, which is 1 space away. So we put it there, so we put 8 there. Now let's look at what happens when we insert 23 this time around. We try to insert 23. 23 mod 7 is 2. We try to put 23 over here. We can't. So we look into the next available space, which is over there. But we've got collision there. So now, rather than looking over here at I plus 2, we're going to look at space I plus 2 squared. So instead, we're going to look at 1, 2, 3, 4 spaces away. So now we are going to go and try and put it over here, right? 4 spaces away from our original point. we put 23 over here. Then we try to insert 3. There's a collision. And then we insert 5, and that just kind of goes straight in. So we had much fewer collisions when we did quadratic probing, although the math was a bit more complicated, just a bit more complicated. The last question was on double hashing. We did not cover.
When it exceeds the table down,
You wrap around.
you do. Okay.
You wrap around, which can make it a bit of a issue.
Your count stays whatever it is, but you just keep going.
Yeah,
Okay.
which makes it a bit of an issue if it's like super full up, right? Because you can keep skipping over that space. So, so don't let it get full up, right? Now, double hashing, basically you have a secondary hash function if you can't fit it in the first space. But we'll go ahead and pass that because that's not something we went over. So now, part 3, part 3, graph algorithms. So perform a depth first search of the graph above, breadth first search of the graph above. Dijkstra's algorithm on the graph above, right? So, and here it will, and here of course they're just totally joking with us because it says to start from vertice C. Also, it's telling us to break ties, not alphabetically, which is the way I'd like to typically do things, but to break ties by using the smallest edge to break ties, right? So, for instance, so we're going to start off at C, right? And we want to do a depth first search. I have 3 possible paths to go down for my depth first search, right, to start down, right? And the way I'm going to choose it is which path has the smallest weight. That's what it says how to break ties, right? If it's just a regular depth first search, you don't really care which one to choose. But this one says break your ties using the smallest edge. So C to B. So we go start at C, then we go to B. Let me go ahead and pull up a text editor to get my to write down my answers. Small. There we go. And here what they're asking for is not the finish order, but the order in which stuff is visited, right? The order in which they're visited. So not the order in which it's popped off, but the order in which it's visited. C, then we visit B. Now from B, we have 5 choices as to where to go. We could go from B to C, but we've already been there. So we're actually not going to do that. So we actually have 4 places we can choose from. 18, 20, 17, and 13. 13 is the cheapest, so we're going to go to A. So now we're at A. A has 2 choices of where to go, but one's we already traveled along. Brings us back to B. So we're going to go to this one. And it's cheaper anyway, so we'll go that way anyway. D. Now we're at D. D has 2 ways to go, but we've already seen both the nodes that it's connected to. So we're at a dead end. So we backtrack to A, which was now a dead end. So we backtrack to B, which is not a dead end. We've been to C, we've been to A, we've been to D, but we've not been to E or F. So let's go to E or F. F is cheaper, so we're going to go to F first, which is a dead end, right? We've been to C and B already. So we backtrack to B. And then we have only one choice left, which is to go to E, which is a dead end. So we backtrack to B, which is a dead end, which we visited everything that we can get to from B. And we backtrack to C, which we were able to use to travel to, which would only be able to travel to everything else that we've already visited. So we're done with C. So we're done there. So we'd go, so this is our path. C, B, A, D, and then we'd backtrack and visit F, and then backtrack and visit E. Right, this is the order in which you visit stuff. If we wanted to know what order we pop stuff off, the finish order, it would be D, A, B, and then we would go to F and pop that off, and then E and pop that off, and then finally pop offs. D, A. Sorry, messed it up. My bad. We would start here. We'd go to D, pop off, pop off. We'd not pop off B yet because we have other neighbors to go to. So we'd go visit F, pop that off, E, pop that off. We're done with D, B, pop it off, and then finally pop off our starting point. Right.
How do you get from F to F?
Sorry?
You go to D, A, F, how do you do?
Here. No, this is for the finish order, the order in which stuff would be popped off.
D, A, F, then.
Yeah, D, A, E wouldn't be popped off.
Okay.
So pop off F, pop off E, travel to F, pop off F, travel to E, pop off E, then pop off B, and then we're done at C. Now this may look confusing and intimidating, and you'd be wondering, how in the world am I gonna, maybe you're worrying about having to study this for like a half an hour in the final, and I'm here to assure you, don't worry about that. It's not, the depth first search is not on the final exam. Okay. Why? Because I've already tested you guys with it with a homework assignment and another homework assignment, right? You've already had 2 homework assignments on depth first search. I know you can do depth first search. Okay. On the other hand, so why waste time on it? On the other hand, breadth first search and Dijkstra, you bet your tuchus that they're going to be on the exam. So let's start off with the breadth first search. Breadth first search, fortunately, is actually pretty easy, and we can kind of eyeball it, right? The idea here is we're going to start at C, then we're going to visit all the one-step neighbors of C, which are B and F, and then we're going to visit the and E, right? Here's our one-step neighbors of C, and here's our two-step neighbors of C. Now we just got to make sure they're visited in the right order, right? But it's going to be a permutation of this plus concatenate with the permutation of this, concatenate with the permutation of this. So let's start out at C. We need to visit our cheapest neighbor first, which is B. Then we visit our next cheapest neighbor, which is E. And then our next cheapest neighbor, which is F. So B, E, and F, right? Cheapest neighbor, then visit my next cheapest neighbor, then visit my next cheapest neighbor. Why are we doing it by cheapness? Because we're breaking our ties by... We're breaking any ties by the cost of the weight to travel along it. It just so happens that also happens to be alphabetical in this case, right? Then we'll go and visit B next. Then we'll go to E and F and check all their neighbors. B's neighbors are A and D, so we'll visit A next, then D next, because that's again, A is cheaper than going to D, and so we're done with A and D, so we would visit them next. We visit E. There's nothing new that E would add. There's nothing new A would add. Sorry, F would add. There's nothing new A would add, and there's nothing new D would add. So this is the final order which we would do a breadth first search. We'd go.
If those other ones could add something, would it still be all of these first, or would it be by weight at that second, at 2-step level?
So say there was a X right below E, right? There was an X with a cost of 2 right below E. Make it really cheap, right? We would still be visiting, the order would then be A, D, X, because we'd go to B first and visit its neighbors, then we'd go to E and visit its neighbors, then we'd go to X and visit its neighbors.
So then the cost for a single step. Okay.
So now let's look at Dijkstra's algorithm. The final one, definitely Dijkstra's is on the exam. It may even be on another exam you take, like depending on, I don't know, if you're taking like math concepts and they're covering Dijkstra's, and they'll probably be on an exam, because Dijkstra's is always on an exam if it gets taught, because it's an important algorithm. All right, so Dijkstra's, again, it is a fairly, actually there's no real need for me to do it on the board. I can just do it over here where my handwriting is better, right? So, right, we have 4 data structures for Dijkstra's. We have our set of stuff that we figured out the shortest distance to, our done set. We have the to-do set, right? The stuff we still need to figure out the shortest distance to. And then we have a table that we need, which is the node, distance, prev, right? Now let's go ahead and look at what we need to do for Dijkstra's. It says is to find the shortest path from D to vertex E. Now to find the shortest path between 2 nodes in a graph, you have to check all of them out. You got to make sure, because one of those nodes you may not have visited might have something shorter, right? So list in the order in which they become known all vertices to which the shortest path is determined in the solving process, and the length of the path to each of these vertices. Our table will be able to figure it out than us. So this is starting at D to E. So that means that done So that means we're going to start over here and find the shortest path to all these guys. So done is D, and to do A, B, E, F, C. I'll go ahead and make it alphabetical. Right? And then we'll just list down our nodes. A, B, C. We don't have to put down D because that's our origin point, right? So it'd be kind of boring. E and F. So now we need to finish initializing by initializing our initial distances to all these nodes. Our initial distance to A is 10, and we get there from D. Our initial distance to B is 17, and we get there from D. And then our initial distance to everything else is infinity, which we get to from D, right? That's how you list, right? It costs infinite cost to get from D to all the other nodes because we don't have a discovered path, right? And that's a placeholder value, right? It's very useful to say if there's not a connection that it costs infinity to get there. All right, so let's look at, so now what we do is that we go through all these nodes that we in to do and find which one has the smallest value. That one we've discovered the shortest path to, right? So D to A is 10, D to B is 17, the rest are infinity. So D to A, we figured out the shortest value to. We've done that. So now let's see if A gives us any more information. A has two edges, one which leads back to our done set and one which leads to B. Is 10 plus 13, the cost to get to A plus the cost to get to B. Is that any cheaper than what we currently have for B? No. 23 is, so we don't update that one. All right, so we're done with A. So the next value that's smallest in here is 17 because it's smaller than infinity, right? So now let's look at all the edges that B has. So let's look at B to C. It costs 17 to get to B, and then a 5 additional to get to C. So that's 17 plus 5. Is that cheaper than infinity? I hope so. I mean, I'm not a mathematician, but I mean, I'll go for it and say, yeah, I'll go out on a limb and say that's smaller than infinity. So we get to C for a cost of 22 by going through B, right? What about going to F? 17 plus 18, that's 35, which is smaller than infinity. So 35. And we'll go ahead and put down B. And then to get to E, that is 17 plus 20, which is 37, going through B. And that is also smaller than infinity. So we're done with B. So now let's look at all these other values. C, E, and F. C, E, and F, which of these is cheapest? 22 is the cheapest, which belongs to C. So C. So it costs 22 to get to C. 22 plus 22 to get to E. That's 42. Is that cheaper than what we have currently for E? No, it's not, so we don't update E. 22 plus 30 is 57. That's not cheaper than what we currently have for F. So we're done with C. And then both F and E, well, sorry, we'd select F next and then E. But neither of those nodes will provide us any additional information because their edges all lead back to our done set. So with that, we're done. This is the order in which we've discovered the shortest path to all the nodes, right? Because that just happens to be what I listed out. And here are the shortest paths. Sorry, these are the costs to get to each node along the shortest path, and this is how you get there. You get to F by going through B. How do you get to B? Well, let's look. B says you go through D. How do you get to D? Well, D's our origin point, so that tells you everything you need to know. That's how this whole previous structure works. All right, so there's another page with this graph, but it talks about Prim's algorithm and spanning trees, which are fairly straightforward. They're just not something I went over because I prefer to go over topological sort instead. All right, so now into the really interesting stuff, just making sure what time it is, coding. So let's look at a binary tree which has nodes of this current of this type. Public class node is made up of nodes. Sorry, it has nodes which have a key and a data. So kind of like it's more of a tree map than anything. It's a lot like the trees we've been dealing with, only they have two things. They have a key and the data. So kind of like how our index tree had the word and then the list of all the occurrences, right? So you have your key, your data, your left and right. Right? The following below uses recursion to search for a key in a binary search tree, whose root node is referred to by root. If it finds the key, it returns the data associated with it. If it doesn't find it, it returns null, right? This is the search method which we've seen a number of times, right? If I'm null, then return null. Otherwise, if it has the key, return the data. That's the only thing that's different. Otherwise, if the key I'm looking for is less than my key, I'm going to send you to the left. If you're greater than me, I'm going to send you to the right, right? In the space below, rewrite the search method so it uses iteration rather than recursion, which I've always told you is a bad idea. But it's really a bad idea if you're, but let's go ahead and, it's really just a terrible idea if you're using deletion. It's actually not too bad for search. So let's go ahead and see how that would work for search. Okay.
What, using what?
Iteration. So solve this problem without using recursion. So rewrite this method without using recursion, it's saying.
Right, what do you say, elision?
Iteration. Iteration. So in other words, using a loop instead of recursion. That's actually fairly straightforward. Public, static, void, right, we want a data, so that's an object. Public data, public object, search, and the same header is going to be the same. Node, and int key. Okay, so what's next? We have
Is it like you're doing a traversal?
no, I'm searching for a key.
I know, but since they're saying not to,
Use iteration, it's not too bad. So first off, I'm just going to create a what I'm going to do is I have to use a loop instead. So while root, sorry, so rename this to root. While root is not equal to null. While the current node that we're on isn't null, do the following. If we ever hit null, I'm just going to return null. Okay? So here, it's actually going to look a heck of a lot like the recursion. If root.key is equal to, actually technically that should be, to make it in line with what I'm going to do later, it should be key is equal to root.key, but it honestly won't make a difference there. If my keys are the same, return root.data. Otherwise, if key is less than root.key, if my key is smaller, then I would normally send you to the right, but instead what I'll do is I'll just simply say root is equal to root.right. Right? I'll set my current node equal to the node on the right. And now you see that it's actually fairly straightforward. Else root is equal to root dot, should be left over there, not right. Root is equal to root dot left. If you're less than me, I'm going to go to the left and search the node there. Otherwise, I'm going to go to the right and search the node there. And that's how I can do that without any recursion. Now, why did I bother doing it with recursion if it looks pretty simple to do without recursion? Because I was teaching you how to do recursion, and that would be kind of useless if I just, threw you all the. It'd be pretty terrible if I basically built you all the way up with without using recursion, and then we finally hit the delete method, which is a lot easier to do with recursion. And then you get the delete method, and so you're like, where did that recursion come from? That's kind of impossible looking. especially for solving the next problem. Write a method called mirror, which takes a reference to the root node of a binary tree and creates a new tree with its own nodes that is the mirror image of the original tree. So I'm going to do an incorrect version of this first, and then I'm going to rewrite it, right? So for example, if the root is a reference to a tree on the left, then this is what we'd get on the right. It's much easier if you use recursion, it says. So here, right, this is our input tree on the left. On the right, this is our output tree, right? Notice that 3 and 2 have swapped, and 2's children 4 and 5 have swapped, and 5's children 6 and 7 have swapped, right? So it flipped. So every node flips its own children. Let's see. Actually, let's see. Is it more than that? 5 will flip.
Yeah, the smaller is always going right, bigger's going left.
Mm-hmm. Let's see, though. This one's actually quite a bit trickier, I think, because also, let's see. I think also, right, to, oh, no, I'm just going to go, no, that will work itself out. Okay. Okay. So let's go ahead and write this. Public. So I'm going to, like I said, I'm going to write it not so much wrong as like, I'm at a right angle. I'm going to be parallel to the right answer. Public static node mirror node root. Okay, so if base case, because this is going to be done recursive, if I am null, if root is equal to null, return null. Okay, so what do I need to do if I'm making a look? Remember, all this means for everything here with this problem, everything has to be a local decision. Which is actually, that makes it fairly straightforward. If I'm null, I return null. If I exist, I need to swap my children, right? And then tell them to swap their own children. That's actually fairly simple to do with recursion, right? So, otherwise, I will tell my, otherwise, I need to swap my children. Node node temp is equal to root dot left. You caught me. This is why I'm saying this is parallel to the right answer. I'm not making a new tree yet, right? But right now I'm reversing the same tree, the tree I got in. Root dot left is equal to root dot right. Root dot right is equal to temp, right? That will swap my children, right? And then mirror root dot left mirror root dot right. But again, this is an incorrect answer because I'm like, wait, I'm supposed to be my first warning is, wait, I should be returning a node. I don't really see what I need to be returning for these. And then I get here and I return root. Are we sure I don't need to do more? Double check the problem. Well, this swaps the original tree, but it says that I want to make a new tree with its own nodes. That's a bit trickier. So let's go ahead and I'm just going to keep this around so I can reference it, but let's go ahead and start and modify this other one. Right, so obviously, if I'm equal to null, still same answer. Otherwise, what do I need to do? Well, then I need to, so rather than just saying, oh, if I exist, so if I'm null, I return null. Otherwise, I need to make a copy of myself. So node new root is equal to new node, and let's just assume the instructor the constructor works like this. Root dot item, right, or whatever it is. New node root dot item. Okay. New node new left is equal to let's see, new node root dot left dot item, except that, oh wait, I can't assume that my left node and my right node exist, right? Oh, that's not too bad actually.
But we're going to do the other one.
Ah, that's fine. So actually, we can actually shorten this because I can't assume what my children are going to be. So I just create a new copy of myself, and then then I make my, then what I'm going to do, I'm going to say new root dot, my left child is going to be mirror the old right child, and then new root dot right is going to be a mirror of the left child, right? And they'll create them, and if they don't exist, they'll return null to me. But if they do exist, they'll return a copy of themselves, and then they'll handle swapping their children around. And then I'll pass myself back up to my parent to tell them, hi, here I am. So that makes it fairly. So that's basically as concise as I can get it. And during the first couple class, I did this. The first time I did this, I actually made that mistake unintentionally, and so I had to go back, and it took me about 10 minutes to do.
Do you
Yes.
still return a root, or do you return a root?
Ah, excellent question. Should definitely return new root here. All right. Finally, dreaded question over here. What's the big O of that method that I just wrote? Well, it's a tree, and there's two types of methods in tree. A searching method or a traversal method. Did this search the tree or did it traverse it? It traversed it. We went over every single node in the tree. So that cost how much time? O of n time, right? We copied every single node in the tree and flipped their children. That's O of n, right? We did a set number of operations for each single node. So it's O of n. So that's that practice exam. So let's go ahead and take a break here. And so